Now, any questions before we start, or comments, etc.? So, first of all, are you familiar with divergence, curl, etc.? Now, basically what we have is, for example, if you have some function, an arbitrary function u, if you look at its change, a very small change, when you change the point that it is evaluated at, this is equal to gradient of u dot dl. In a sense, this is the definition of the gradient. And similarly for the divergence and the curl, if you have a vector field, if you take its divergence, now if you have a vector field, take its integrated over a closed surface, this is equal to the divergence of that vector field integrated over the volume. So here we have, there's a closed surface, it encloses a volume, and here we have the integration over the volume, here we have the integration over the boundary of the volume. Oops. Let me make this a bit smaller. Okay. Now, this is basically, again, the definition of the divergence. And finally, if you have a line integral, if you have any vector field integrated over a closed loop, then this you can write it as the curl of that vector field integrated over the area bounded by this loop. So here we are integrating over some area, and then the left-hand side, the closed loop, is nothing but the boundary of that loop. So del A is just the boundary of A. If you have an area, the boundary of an area is just a closed loop. If you have a volume, this is the boundary of the volume. The boundary of a volume is just a closed surface. In fact, I mean, you can even change the first one. If you just look at, let me say, UA minus UB, this is equal to the integral of the gradient of U dot dl from a point A to the point B. So basically here, now in all these relations, in both three of them, you have an integral over a region, which is, the integrand is some kind of a derivative, either a divergence or a curl or a gradient, and that integral you can write as the difference of in the boundary. If you have a line, the boundary is just the 2 points, and you are integrating over those 2 points. Just means you just take the difference of the value of the function. Here, if you have a area, you are integrating something over an area, then you can, if it is a derivative, then you can write it as an integral over only the boundary. And similarly for the volume, if it is a derivative, you are integrating over a volume, you can convert it into an integral over the boundary. And by the way, these are the definitions. They are not proofs, these are just the definitions, how we define the gradient, divergence, and the curl. And in fact, using these definitions, it's quite kind of easy to obtain the expressions for the divergence, curl, and the gradient in various coordinate systems. I mean, in Cartesian coordinates, they are kind of easy. You can identify this operator, vector operator, in the x direction, del over del x, plus in the y direction, del over del y, plus in the z direction, del over del z. In that case, the gradient of a scalar function just turns out to be a vector whose components are the derivatives of your function. If you have a vector field, scalar product in terms of the components just looks like ordinary scalar product. The x component of this operator is just del over del x multiplied with the x component of the vector field A, plus the y component of the vector operator is del over del y, ay, plus del over del z, az. And the curl just looks like as if that operator is an ordinary vector. This would be equal to, you can write it as a determinant, x hat, y hat, z hat, del over del x, del over del y, del over del z, ax, ay, az. But of course, this is true basically in the Cartesian coordinates. If you try to write these expressions in cylindrical or spherical coordinates or in some other coordinates, it gets really messy to obtain their expressions. But nevertheless, just using these definitions, you can just obtain their expression in an arbitrary coordinate system. Now, I would advise you to check Appendix A in Griffith's Electrodynamics. Now, in the appendix, there's a nice discussion on how to obtain the divergence, curl, and gradient in various coordinate systems. But I do advise, you don't have to memorize their expressions in different coordinate systems. In the exam at least, I will definitely give you their expressions if you need them. But nevertheless, I think it's illuminating to see how they can be obtained from the definitions. Now, these we will be using quite often. Now, there are, of course, these are essentially, these just replace the, in one dimensions, we have a single derivative. These are just generalizations to more than one dimension of the first derivative. So, of course, if you go to more than one dimension, you can have scalar functions, that those are functions that have, whose values are just numbers, or vector functions. Those are functions which have their values as vectors. So those are the two simplest possibilities. By the way, these we will be calling them as fields. Now, the definition of a field is just a function defined in all of space. That's what we mean when we call something a field. We will be talking about, for example, the electric field. Well, electric field is nothing but a function whose values are vectors, and it is also defined in all of space. That's what we will be. From now on, we will be just calling them fields. Well, if you have scalars and vectors, well, this derivative operator itself is a vector, so you can multiply it with a scalar and obtain a vector. You can take the scalar product of it with a vector and get a scalar, which we call the divergence, or you can just consider the cross product of this derivative, which is itself a vector, with a vector, and obtain another vector, which we call the curl. Now, also, if you just go back to their definitions, these are kind of tell you what they mean. Now, the meaning is just this one. For the gradient, if you look at the gradient, now the gradient basically tells you how your function changes as you just change your point slightly. Now, furthermore, you can, just using the definition of the scalar product, you can just write this as gradient of u, the magnitude, times the magnitude of dl, times cosine of the angle between the two. So basically, if you imagine that you keep the magnitude of dl constant, just imagine you are at a hill and you are taking one step, then the u will be the height, your height from the ground zero. Then this du will be, if you take your step in the direction in which the hill is steepest, then your height will change the most, right? So you are on a hill, and you are looking at change in your height after you take one step. If this is your hill, if you take a step this way, your height will not change. If you take a step this way, your height will change, but it will be a negative change. But if you step this way, then your height will change the max after you take one step. If you look at this function, that happens when cosine theta is 0. That is, if cosine theta is 1, then theta should be 0. If theta is 0, that just means that your step is in the same direction as the gradient of your function, u. So that basically tells you that the gradient of a scalar function gives you the direction in which your function changes the fastest. So that's kind of an interpretation of the gradient of a scalar function. Now, if you look at the curl of a function, this is the curl of a function. But to interpret what that is, just look at this one. You have your function, you are integrating it over a closed loop. If your vector field itself curls around that closed loop, then this integral will be maximum. If your function doesn't curve around your loop, but mainly, let's say, goes straight in one dimension, then this a.dl will be positive in certain regions, negative in certain other regions. So this integral will be either very small or 0. So basically, in that sense, the curl of a function measures how much your vector field just curves around around the point. So one example would be, if you remember the magnetic fields. Let's say this is our wire. If you remember from your 110 or 106 courses, the magnetic field created by this wire is in which direction? Clockwise or counterclockwise? Counterclockwise. So curl of B in this case is non-zero. But if you look at the electric field, because curl is non-zero because basically your magnetic field is rotating around that point. If you look at the electric field lines are radially out. It is not curling around any point. So the curl of the electric field is 0. So that is vaguely, let's say, what the curl is measuring. The reason why I'm saying that it is vaguely somewhat measures how much your field curves is that if you look, we will be calculating the curl of B is equal to 0 if R is not on the wire. Now, this is kind of a weird, although it is curve. Well, this kind of tells you that these lines are curving around this point, not this point. So if you measure it around here, it is 0. If you calculate this curl of B around this point, it is 0. Around this point only, it is non-zero. So in that sense, the curl measures how much your field is rotating around some point vaguely. There are some subtleties that you should keep in mind. Now, if you look at the divergence of a vector field, you see, the divergence of a vector field, when we integrate it, we relate it with a volume integral of the vector field itself. So just similarly, if you assume that your vector field is always perpendicularly outward from that surface, then this integral will be maximal, since E is perpendicular to ds. And hence, divergence of E would be large. So if, again, vaguely, if your field is kind of diverging from a point, in that case, the divergence will be large. And If we go back to these examples over here, the magnetic field is not diverging from any point. So divergence of B is 0. But if you look at the electric field is diverging from a point. So divergence of the electric field is non-zero. And again, the electric field is diverging from this point, let's say r equal to 0 point. Divergence of the electric field is equal to 0 if r is not equal to 0. If we evaluate this divergence of the electric field, we will get 0 unless we are evaluating at this point. Now we can talk about the second derivatives also. Now the second derivatives, well, we have this derivative operator, which is a vector. So there are various combinations we can form. If you take, for example, this is the first derivative of a function, so you can calculate the curl of this function. You can talk about the divergence of this function. Then we had the divergence of a vector field. And now we said that since this is itself a vector field, the divergence, we can take its divergence, which will be a number, or we can say take the divergence of a vector field and calculate its curl. Then we can have the curl of a vector field. This is itself a vector field. We can talk about the divergence of this curl, or we can talk about the curl of a vector field. So basically, these are all possible second derivatives we can think of. Now let's try to simplify some of these and see what they are explicitly. Now let's start with the second one, divergence of a gradient. But I mean, you are familiar with index notation, right? Okay, so let's use the index notation to simplify it. I mean, your book doesn't use the index notation, but one of the problems that the students are facing in studying electrodynamics is that you have to remember all these vector identities. But with index notation, the derivation of those vector identities is just a couple of lines most of the time. By the way, I will upload all these notes in Note class. So if you don't want to write, you don't have to write. Well, let's start with the divergence of the gradient. Well, the divergence, this operator, gradient operator, in index notation, it's just a derivative. That is the ith component, let's say. Or sometimes, just to simplify the notation a bit, I will just denote it by del I, meaning that it's the derivative with respect to the ith component. So the definition of a scalar product in in index notation is just, so this is equal to the ith component of this one multiplied with the ith component of this one. This is equal to del I. Well, the ith component of the gradient is nothing but del I phi. This is, you just take the second derivative with respect to the x, y, z components. And since I is repeated, I don't write the summation sign actually here. There is a summation sign. I is equal to from 1 to 3. But we are just ignoring that summation sign. Whenever you see an index repeated twice, we will understand that there is a summation over that index. Now, if you write this explicitly, del by del squared by del x squared plus del squared by del y squared plus del squared by del z squared phi, which we will just call the del squared phi. This is what we call the Laplacian. Now let's go back to the first one. Curl of a gradient. This is a vector. This is supposed to be a vector field. So let's look at the ith component of this vector product. Now, in index notation, the vector product, the components of the vector product, if you remember the explicit expression, there are all these plus or minus signs. And those plus or minus signs we keep track of by what we call the Levi-Civita tensor. I mean, by the way, if some of the notations are not familiar, just let me know.
Can you repeat the name?
Hmm? The name, this is the epsilon ijk, is called the Levi-Civita tensor. Basically, epsilon 1, 2, 3 is equal to 1. Epsilon ijk is equal to epsilon jki, which is equal to epsilon, well, let me write it this way. Epsilon ijk is minus epsilon jik. If you change any two indices, it changes sign. So basically, epsilon 1, 2, 3 is equal to minus epsilon 2, 1, 3. This is equal to epsilon 2, 3, 1, etc. So basically, in the cross product, you have all these plus or minus signs. So this Levi-Civita is either plus 1 or minus 1 or 0 if any two indices are the same. So it keeps track of all those plus or minus 1s or 0s. Okay? Epsilon ijk, the j component of the first vector, and the kth component of the second vector. So this is the I component of the curl of the gradient. Now in this index notation there is something funny, well, funny but nice, let's say. If you have something symmetric, and something anti-symmetric. Of course, these S and A can have any number of indices. It's important that they are symmetric in a pair and anti-symmetric in a pair. And if you just multiply them, this is 0. So here this ij pair is symmetric. In A, the same ij pair is anti-symmetric. The product is 0. Now the easiest way to see it is, let's say this is equal to, and remember we are summing over I and j. So I and j are just dummy indices. Since they are dummy indices, I can just change their name. So the index I can just call it j, and the index j, I can just call it I. This is equal to sji aji. This is equal to now I will just, in S, it is symmetric if I change the positions of I and j, and A is anti-symmetric if I change the positions of I and j. So now I'm not renaming them, I'm just changing their positions. So this will be equal to Sij times minus Aij. But you see, I started with Sij Aij, summed over I and j. I ended up with Sij summed over I and j with a minus sign. So I get the same thing with a minus sign. So something is equal to minus itself only if it is 0. So this just tells me that Sij Aij, this is equal to 0. Well, where will I use it? Let's see. Epsilon ijk. If I change the positions of j and k, we said that by definition it is anti-symmetric. It changes sign. So epsilon ijk is anti-symmetric in j and k. The derivative with respect to xj and the derivative with respect to xk, Well, the derivatives, I can change their order. So that second derivative is symmetric under the exchange of j and k. So I have one object that is antisymmetric, the other object that is symmetric. I'm multiplying them and summing over these symmetric and antisymmetric indices. So it is 0. So the curl of a gradient is always 0, with the assumption that you can change the order of the derivatives. Well, for physical cases, we are always allowed to change the order of derivative. Well, let's continue. So we already proved that this is 0. This is we defined as the Laplacian of our function phi. Well, let's look at this divergence of divergence. Well, sorry, this doesn't make any sense. It is the gradient of a divergence, because the divergence of a function is just a scalar number. We cannot take the divergence of a scalar number. It's the gradient of a scalar function field. We have the gradient of the divergence of a vector field. Well, this is a vector field. Let's look at the I component. Now, the I component of this field is nothing but del I times the divergence of A. Now, the divergence of A is del I del j aj. Well, there's nothing much we can do over here. It is what it is. It just stays as it is. Well, we don't really see this expression often in physics, so we don't even have a special name for it. So it just stays as it, no simplification. Let's look at the fourth one. It is the curl of a divergence. Nope, sorry. Curl of a divergence doesn't exist. Divergence is just a number. It's a scalar function. You cannot take its curl. Divergence of the curl, this exists. Well, we just multiply the scalar product just tells us that we have to multiply the corresponding components and sum them. Del I times curl of A, the I component. This is del I. Well, the I component of the curl is, again, we will use the epsilon tensor, epsilon I j k. Del j ak, or let us write this as epsilon I j k. Del I del j ak, which is, it is 0. Again, if you look at the epsilon I j k, it is antisymmetric if we exchange I and j, the first two indices. But if you look at the derivative with respect to xi and xj, since we can exchange the order of derivatives, as long as we can exchange the order of derivatives, it is symmetric. So this will be 0. So let's go back. So this is also 0. So what we had find is that the curl of the gradient is 0. The divergence of a curl is 0. And finally, we have this sixth one, the curl of a vector field. Curl of A. This will be the longest one. This is a vector field. So let's look at the I component of the vector field. This is equal to epsilon I j k, the j component of the first vector, times the k component of the second vector. Again, we have the k1 component of a vector field. So let us also write it out explicitly. Del J epsilon K, let me use the indices L and M. Okay, here there is one thing we have to pay attention to. Since J and I are just dummy indices, so we shouldn't reuse dummy indices in a given product. So I cannot call that epsilon Kij, because I appearing in the second Levi-Civita will be different than the I appearing in the first one. So I have to use some different indices, not to make any mistake. And since they are just dummy indices, I can just name them whichever way you like. Del L A K, this is equal to, well, I can, in the first Levi-Civita, I can first exchange K and J, and then exchange K and I, and bring the K to the first place. Why? Well, I like it that way. I bring the K to the first place. I made two exchanges, so no sign change. Yes? LM, you're right. So this is epsilon Kij, epsilon KLM, del J, del L, AM. Now I have the product of two Levi-Civitas. The product is, since Levi-Civita itself is either 1, -1, or 0, the product is also either 1, -1, or 0. Furthermore, we already know that Kij, one should be 1, the other one should be 2, the other one should be 3, if it is to be non-zero. Well, similarly, KLM should also be 1 should be 1, the other one should be 2, or the other one should be 3. Well, K's are equal in both Levi-Civitas, so Ij should be equal to Lm. Either I should be equal to L, or J should be equal to M, or I should be equal to M and J should be equal to L. Otherwise, for no possible value of K, Kij will be equal to 1, 2, 3, and KLM will be equal to 1, 2, 3. And depending on which way they go, the product is either +1 or -1. And so this is equal to Kronecker delta IL, Kronecker delta JM, minus Kronecker delta IM, Kronecker delta JL. Del J, del L, AM. Let's multiply them out. Kronecker delta IL multiplied with del L over here, it just gave me del I. Kronecker delta Jm multiplying with derivative with respect to xj and am. Well, this Kronecker delta, you are familiar with Kronecker delta? It just, Yes. It just tells me that since I'm summing over j and m, I have two summations, but in this summation only the terms j is equal to m contribute. And if j is equal to m, if you look at over here, what I'm actually doing is I'm taking the derivative of j's component with respect to xj and summing over j. That is just a divergence. Or let me write it explicitly, del j am aj. Minus, now this Kronecker delta Im multiplied with am tells me that when I'm summing over m is repeated, so there's a summation over m. Only the term m is equal to I survives. And here I have Kronecker delta jl multiplied with derivative with respect to xj and xl. Again, this derivative, this Kronecker delta tells me that only the j is equal to l terms survive. So this is del j squared. So this is equal to, okay, this is the I component of the gradient operator. This is the divergence of A. Well, the second derivatives we defined as the Laplacian operator. And the I component of the vector I, this is the I component. And so the curl of a vector field we can write it as the gradient of the divergence of A minus the Laplacian of A. Well, this is A. Since we had proven that the I component of the left-hand side is equal to the I component of the right-hand side, I is an arbitrary component, so all of their components are equal. So if you have two vectors whose components are equal, so they are equal. So if you look at over here, well, let's go back here. We said that this is equal to gradient of the divergence of A minus the Laplacian of the vector field. So basically, we end up having only two different second derivative operators. One is the Laplacian, the other one is the gradient of the divergence. Everything else we can write in terms of those two. And similarly, if you have, I don't know, for example, the curl of A cross B. Just using index notation, you can also calculate this curl of A cross B. Just do it as an exercise. Let's do another example. Now, you probably already remember that the potential corresponding to a point charge is 1 over r. It's a scalar field. Let's calculate the gradient of 1 over r. Let's start with the I component. This is equal to del I of r to the power minus 1. Or let's write this as del I times xj squared raised to the power minus 1. 1 over 2. This is equal to minus 1 over 2 times xj squared raised to the power minus 3/2 times del I of xj squared. I just use the chain rule.
Why do you place R by itself?
Well, I'm taking derivative with respect to xi, so I just wanted to show the xi's explicitly. R is a function of xi. This is equal to minus 1 over 2. Well, now I have, since I'm not I will not be doing any manipulation on this one anymore. I'm just replacing it with r. 1 over r cubed. Now I can take the derivative. Again, I will use the chain rule. It will be twice xj times the derivative of xj with respect to xi. Well, these 1 over 2 and 2, they will cancel. Let us proceed. This will be equal to minus xj over r cubed. Now, that derivative, if I is equal to j, it is 1. If I is different than j, it is 0. So if the derivative of x with respect to x is 1, but the derivative of y with respect to x is 0, the derivative of z with respect to x is 0. So the function that has this property is nothing but the Kronecker delta. This is Kronecker delta ij, and remember I have a summation over j. So when I'm summing over all j, this just becomes minus xi over r cubed. So I have this gradient of 1 over r. It just turns out to be the I component of this one is minus r vector over r cubed, the I component of this vector. So what we now have seen is that the gradient of 1 over r is minus r over r cubed, or minus r hat over r squared. Well, again, if you remember your general physics course, the gradient of the potential is supposed to give us the electric field. And the potential of a point charge is 1 over r. The electric field is 1 over r squared in the radial direction. So essentially, this will be relevant in that case. This is something that we will be using quite often. Let's do one more thing. Let's calculate the Laplacian of 1 over r. The Laplacian, if you remember, we had defined as the Laplacian of a scalar function is the divergence of the gradient. This is equal to the divergence of the gradient we had already evaluated, minus r over r cubed. So this is equal to that I, let's write it in terms of the components, minus xi over r cubed. This is equal to minus, well, first let's take the derivative of xi with respect to xi. It is Kronecker delta ii times 1 over r cubed plus minus xi. I will use the chain rule for the derivative of 1 over r cubed. It is minus 3 over r to the 4 times del I of r. Well, I will not repeat the calculation, the derivative with respect to xi of r. We had already done it over here, but that was r squared. So this will be equal to minus Kronecker delta ii 1 over r cubed plus 3 xi over r to the 4. And this derivative is just xi over r. Okay, what is Kronecker delta ii? 3.
Yeah.
Remember, I is repeated. So there is a summation over I. For each possible value of I, Kronecker delta ii is 1, but we have 3 terms in that summation. So Kronecker delta ii is 3. This is minus 3 over r cubed plus 3 r squared. Xi squared is r squared divided by r to the 5. This is equal to 0. So Laplacian of 1 over r is equal to 0. Any questions on this derivation? Let's look at one more thing then. We have this Laplacian of 1 over r. We had seen that it is 0. So its integral over any volume should be 0. Right? Let us integrate it over the sphere of, let's say, radius large r. Okay, if we just put 0 over there, then it is 0, and we are done. Let's calculate it in a different way. This is my volume V. This is equal to, well, the Laplacian we had defined as the divergence of the gradient of 1 over r. But the divergence, the integral of a vector field, the integral of the divergence of a vector field over a volume, we can replace it by the integral of the vector field over the surface of that volume. Now this ds will be equal to if we take a very small surface element, it will be, let's say, its magnitude in the radial direction. Right? So this will be equal to del V dot r hat in the radial direction. Now, we didn't write it explicitly, the expressions for this gradient divergence curl in various coordinates, but in spherical coordinates, the divergence of a function is in the r hat del phi by del r plus other components in the theta hat and phi hat, but at least in this problem I don't need them because I mean they are both all perpendicular to r hat. So this is equal to, on the boundary of the volume, derivative with respect to r of 1 over r times ds, the surface element. This is equal to the integral on the boundary of minus 1 over r squared. You see, now I can replace it with large R squared because I'm integrated over, at least in the simple surface, I have chosen it to be a sphere. So every point on the surface, its radial distance is capital R. So everywhere on the surface, R is fixed. Times ds. But capital R is just a number. It is constant. I can take it out. What remains is the integral of the surface, and the surface of the sphere is 4 pi r squared. Well, r squared is cancelled, so this is minus 4 pi. So we started by saying that Laplacian of 1 over r is 0, but its integral somehow is non-zero. And that we will continue in the second hour. Yeah, any questions up to this point? Now we will see. There is a mistake we did in our derivation. I mean, you can go back and in the break you can try to find what mistake we did. There is a mistake we did, or let's say there is an assumption we made, and hence our result is not exactly correct. So we will correct our calculations in the second hour. We will see that Laplacian of 1 over r is not really 0. Because its integral is non-zero, it cannot be 0. Okay, see you after 10 minutes.